Okie dokie, chemists, let's get started now. Can you hear me now? Yes, okay, all right, let's get started. Plan is for today is to finish chapter 14. The last part, mechanisms, the catalysis, this last part's not going to be on midterm 2, but I've incorporated some review things in the remaining slides as well, so we'll touch back on concepts from earlier in those last couple slides of chapter 14, and then the plan is to do some chapter 13 review in preparation for our midterm this Friday. So remember, our midterm on Friday is in recitation. The majority of you will take it in recitation. If you're SLDS, it's your responsibility to set up your own appointment. I've already emailed those of you who haven't set that up. So do set that up within the correct time window. So we'll review a little bit after we finish chapter 14. I doubt we'll get into chapter 15. Today we'll probably start that on Thursday. And so, yeah, the plan is to incorporate some review for our midterm today and on Thursday, but also introduce a little bit of new material as well, but we're not going to go as fast. So some announcements before, because we got to keep moving. Some announcements before we get into things. What is this? Okay, so I placed the Lockdown Browser test quiz in one of your assignments to ensure that you do it. It's not for a grade, like it's in a category that's weighted 0. It's the only way I can get it to show up on your assignments list. It's the only way I can get it to show up on your calendar. So I have that due date for you all by next lecture. I want you to test your device that you plan on taking your exam on with that Lockdown Browser test quiz. You'll see the question types, you'll see what Lockdown Browser looks like. You can test out the calculator function on Lockdown Browser if you want to do that, but I need you to do that by Thursday. If you don't, I'm going to be emailing you to get that tested. I don't want you to walk in on the midterm on Friday and your device not work. Because here's the problem. Now with exams and recitation, I can't help you. Right? So if you're with me before, I would run around like a chicken with my head cut off, trying to help students get started on the exam, because I know that your biggest concern is starting the exam on time, and I try to help you, but now I can't help you. So do test your device. And I'm going to say, even if you tested, you know your device worked last semester, still test it. Just test it to make sure that when you go into the exam, everything will start up great. All right, I'm going to annoy you if you don't have that done. Next, my review session is tonight at 6 p.m. Bring your friends. It's in your calendar. You should see the links for that. It's in this room. It's on Zoom, and I record it, yada, yada. Friday is your midterm in recitation, so be prepared with your device. Make sure you have that approved calculator. These are the series TI 30, 83, or 84 only. Yeah, so the most common unapproved calculators are Casio calculators. I know they look like dumb calculators, but this is the policy, so no Casio calculators. The TI Nspire, that's not an approved calculator. And the last one, the TI 89. That is also not an approved calculator. So do make sure you have one of these. If not, the TA is instructed to take your calculator away. There is a calculator inside Respondus. It's just annoying to use. All right, make sure you have a pen or pencil for use of the scratch paper that you'll be given. I've already posted the exact copy of the supplemental information that you'll get at the exam. Make sure you have a photo ID. Buck ID is the easiest. Like a passport, a driver's license, anything with your face and your name on it. I'm not sure if they accept the ones on the phones, like the Buck IDs on the phone, so don't count on that. Bring a physical ID with you so your TA can confirm your identity, your device to Duo, and then the last tip is know your OSU password, because Duo does not autofill for you. I've seen it. You've crammed so much information in your head that you just forget your password, so do know your password. All right, so those are the announcements for the exam. And then the last announcement, I hate that this happens always, every term during the first exam. If you're in that GE launch class, all right, and you have to interview someone, and so if you know what I'm talking about, listen. If you don't, then just shut your brain off. I get many, many requests every term to do this GE launch interview. I have too many students, so what I do is just do one big question session, and I want to do this after the midterm. So I've already scheduled this large interview with all the students who are in this GE launch class next week. So next Tuesday at 5:30. All right. So you can come in person. I'm going to Zoom it, and I will record it. So there you go. So those are the GE launch people. Okay. So if you aren't in GE launch, just ignore what I just said. Who's in GE launch and has to do this? Yeah. See, I'm not going to interview all of you individually, and you know why? Because you all ask the same 5 questions. All right, and so here's the thing. I do this interview so I get those 5 questions out of the way so we can ask good questions. All right? Yes, so that's why we do that. Okay, all right, so that's my rant on the interview thing. All right, so the plan is let's finish up chapter 14 and then do some review. Okay, we left off on mechanisms. Is mechanisms on the exam? No, it's not. But is rate laws on the exam? Yes, so we're still learning about rate laws because mechanisms is the last way to determine a rate law of a reaction. So there are 2 ways, 2 types of mechanisms we will study. The first one is where the slow step is the first step. And then the second kind of mechanism is where the slow step is the second step. And so the big takeaway from mechanisms is that the slow step is the rate determining step. The slow step determines your rate law, and that's basically it. And so we see from this example that our slow step is the first step, and so our rate law for this overall reaction is simply the concentration of those reactants, A and B, and that's it. The second step is a fast step. I like to think of it as, you know, the rate of this overall reaction, what you see, it depends on this slow step, because once this slow step is done, the fast step will just take over, slap a bow on that, you know, that reactant, and then you're done. You have products. Where that last step doesn't affect your overall rate because it's so fast, we can essentially just ignore it. And so in this example, we have that first kind of mechanism. The slow step is the first step. Those ones are the easy ones. All right, and so we see in this example, again, we have the slow step is the first step, so we see that the rate law is NO2 squared. This is a second order reaction because we have 2 NO2s in that first step, and that's it, right? So the rate of that second step doesn't matter. And so, you know, we can relate this to previous ideas. If I double the concentration of NO2 in my reaction, how should the overall rate increase or change? If I double the reaction or double the concentration of NO2, what kind of change should I see? A 4 times increase. See, same ideas as before. But what if I double CO concentration in this reaction? Nothing happens because CO is what order of this reaction? It's 0. It's actually in the fast step, and so that implies that the reaction doesn't depend on CO concentration. It's 0th order. So we see no change, but we would see a 4-fold increase with NO2. So same ideas there. All right, decomposition of hydrogen peroxide. So again, we have slow first step. We combined these 2 steps, step 1 and 2, to give our overall process. And we see that 2 components cancel out of the equation, the equations we add up, but a little bit differently. IO minus is a substance that's produced and then consumed in the next step. So IO minus is an intermediate. But on the other hand, iodide in this 2-step reaction does not appear in our overall reaction. It cancels out, but it cancels out differently. I minus cancels out differently where it is consumed in the first step and then reproduced at the second step. So I like to think, okay, catalysts are reactants then products, but intermediates are products then reactants in those steps. So we see that I minus, because it's consumed and then produced by the end of the reaction, that is a catalyst in this reaction. Both of them cancel out, but we have to be cognizant of how they're added to the reaction to identify whether it's an intermediate or catalyst. Intermediates are never added to a reaction. They're always just made in the middle, but a catalyst does have to be added to a reaction. It's part of the reactants, but it ends up getting made at the end, so it gets canceled out. And so we see in this process, again, the easy one, I guess. I hate saying the word easy, but I mean it is. The slow step is the first step. You take the concentration of the two reactants, that's your rate law, you're done. Okay, so let's keep going. All right, we already did this. Yeah, so this is, how can I ask this question a different way? Here I'm asking where in this coordinate diagram is IO minus concentration the largest? So we need to recognize IO minus in this reaction. It's not a product, it's not a reactant, it's actually an intermediate. And so where intermediate should lie is between these first steps. It's created after the first step. So IO minus concentration should be fairly large in point C, because after point C, the second step takes over, it's consumed, and then you make your products at the end there. All right? Okay, so I think that's where we left off, yes. So let's put it all together. Let's do an exam-like question. So this is a new slide. Okay, so I give you a reaction, so 2A plus B gives you CD, and I tell you the rate law is this. All right, so let's say we got this rate law using a different method, and we get that this reaction is first order with respect to B. So this is an exam-like question because it's a way we can get you to do multiple mechanisms in one question, right? Where I'm asking you, okay, which proposed mechanism is consistent with this rate law? So what we have to do is just get the mechanism for both of them and compare, and that's it. So thankfully, these both are, the first step is the slow step. So for this first mechanism, what is the rate? The rate law is always equal to the rate constant, so I'll just say K, but then times what concentration? A, anything else? B, to any powers? Nope, that's it. Okay, perfect. So, is this mechanism consistent with the rate law that was provided? No, they don't match. One's first order, one's second order. So let's hope that the second one is the right one. And we do the same idea. Just get the rate law for the second example. Again, I made it easy because I've only shown one way so far. And that's where the slow step is, again, the first step. So this rate law is K times what? B. Anything else? Nope, that's it. Yes, just the reactant. So which mechanism is consistent with this proposed rate law? Yeah, the second one. Perfect. All right. And so if you look closely here and cancel out all the steps of these two mechanisms, both of them will add up to this overall equation. And so that's kind of interesting. You know, both of them yield the same net result, the same products, C and D, but behind the scenes, behind the curtain, different steps are happening. All right, and so we can observe these steps kind of indirectly via the rate laws that we see. That given this mechanism is first order with respect to B concentration. Okay, so let's keep going. Okay, so we did slow first step. So now let's do slow second step. It's a little harder, but it's not bad, I promise. Okay, so the whole strategy for mechanisms is that the slow step is the rate determining step. The slow step determines your rate law. That's no different for when you have a slow second step and the first step is fast. We just have to do some tricks, all right? So I have a mechanism here. Two A's are combining to make M. A B and an M are combining to make products, where the second step is the slow step. So just like when the first step was the slow step, what we want to do is just say the slow step is our rate determining step. The slow step dictates our rate law. So the rate law for our slow step is K. I'm going to say K2 because it's the second step, times B concentration times what else? M, because M is also a reactant in step 2. All right, so if this was the first kind of mechanism, we'd be done. But we have a problem. M is an intermediate. Do we ever add intermediate to a reaction? No, it's always created and then consumed in the next step. So we can never add M into our reaction, so we need to get rid of it. And here's the trick to get rid of it. We're going to use the first step to help us get rid of it. All right, we can't have M. It's not allowed. It's an intermediate. So the trick to get rid of M is to use the first step, which we recognized as a fast step. It's technically called an equilibrium, and we'll learn more about this to an insane amount of detail in the next 3 chapters. But I'll introduce it now, that in this first fast step, the forward reaction is happening really fast, and the reverse reaction is happening very fast. That's the idea of an equilibrium. So what we can do for using this first step is we're going to say that the forward rate law is equal to the reverse rate law. And so I'll show you what that means. That the forward rate is dependent on the reactants of step 1. So the forward rate is K1 times A, so A squared. That's the rate law for the forward reaction. Now tell me, what is the rate law for the reverse reaction? So the reverse reaction, the products are now the reactants. So what is the rate law for the reverse reaction? It's a rate constant times what? M. So you're essentially setting one side of the equation equal to the other side of the equation with some rate constants there. And so this is the trick. Now we have an expression that has M in it. I can rearrange things to isolate M and then replace it in my original rate law expression to get rid of it. So M is equal to, okay, move stuff around, K1 over K negative 1 A squared. And so it's this expression. I want to plug that in for M because I'm not allowed to have it in my rate law. And so the beautiful thing that happens here is now I can replace M with this factor of A concentration squared, and now I have a rate law that has no intermediates in it. So I'm going to combine those K's together. So K1, K2 over K negative 1 is B concentration, A concentration squared. I know this looks really messy. So I have all these individual K's, which represent the rate constants for the elementary steps. So I'm just going to be lazy and combine all those K's into one K, where that one K represents the overall rate constant for this reaction. So I'm just going to call this K overall. I like to put it in alphabetical order, but it really doesn't matter. So A squared, B concentration. So there is our rate law. We have an overall K that represents all the little K's of the individual steps. But again, it doesn't matter. We'll only ever measure the overall K rate constant for this reaction. A to the second order and B to the first order. And that's the trick, where you still utilize the same strategy. The slow step is your rate law, but you use this trick to get rid of any intermediates that are in there. Because all of the components of your rate law have to be reactants, things that you can actually add to the reaction. You don't add intermediates, you only add reactants. All right, so that's the hard one, all right, the slow second step. Okay, let's put it all together. We learned 2 types of mechanisms, slow first step, slow second step. So let's get the rate law for all 4 of these examples. All right, so determine, is it slow first step, slow second step? What's the strategy there? And the interesting thing for all of these mechanisms, all of them follow the exact same overall equation. All of them, if you add up the steps, give you 2A plus B gives you CD. So what is the rate law for this first one on the left? Rate equals, I'm just going to call it K, times what? A, anything else? B, anything else? No, so this is a second order reaction. Cool. What about the next one on the right here? This one, is it any different? Rate equals K times B. Anything else? Nope. Those ones are the easy ones, slow first step, where you just look at the reactants of that first step. Now the second two are, I guess, slightly harder. I think we just did this one where we recognize, okay, in this second one, the slow step is the second step. So our rate is equal to, I'm just going to call it K. It should be K2, but it's okay. B concentration times M concentration. Am I done? No, we got to get rid of M. So let's get rid of M by using the first step, where I set the rate law for the forward reaction equal to the reverse reaction. So the forward reaction is K times A squared equals K times M concentration. Right? All of these K values, they just combine in the end, so I'm not really keeping track of them. So we can rearrange this and say, oh, M equals, again, a constant times A concentration squared. I'm just saying K is a constant. And we can plug A squared in for the intermediate that we're not allowed to have. And so we can see that the rate law is a K overall times A concentration squared times B concentration squared. And there we go. That's it. All right, so let's do the last one. This one actually is different, I think. Move you over. All right, so slow step is the second step. So what is my rate law initially? Rate equals K times what? M times A. Am I done? No, we got to get rid of M. Got to get rid of M. So what step am I going to use to get rid of M? The first one, because M's in it. And so we can see, all right, the rate constant for the, or rate law for the forward reaction, so K times B concentration equals rate constant M concentration. So basically B concentration equals M concentration, and this allows me to replace M with B concentration in our rate law, right? And again, I'm just ignoring the K's because they're all constants at the end, and so we see that the overall rate law for this last mechanism is rate equals K times A concentration times B concentration. There we go. There we go. So we see that the last two examples, actually all the examples, okay, you know, have different rate laws except these two, where, you know, the orders of A and B concentration differ in our rate law depending on what the actual mechanism is. All right, so we get a variety of different equations and orders from these different mechanisms. Okay, so an infinite number of mechanisms that we could have. Okay, so the question is, okay, how can we prove that a mechanism is correct? Or is it right? So that's kind of like a trick question. Like, is the mechanism right? That's a very hard question to answer because we cannot see atoms. Reactions happen, and these mechanisms, they're just proposals. It's what we think is happening behind the curtain when we can't actually see what's behind the curtain. We can't see atoms collide with one another. So never will we ask you, is the mechanism right? That's not the right question that scientists should be asking. Instead, we say, is the mechanism, the proposed mechanism, consistent with experimental data? Remember, how many ways did we learn rate laws? How many different ways? 3. So often what we'll do is show you a mechanism and ask you, is this mechanism consistent with the data from, let's say, the method of initial rates? Or is this mechanism consistent with What's the other one? The graphical method using the integrated rate laws. And we asked, do they match? Even if they match, it doesn't mean that the mechanism is right. It just means that the data is consistent with one another. So we got to be careful of our scientific language here. We can't promise that the mechanism is right because we can't see atoms colliding with one another. But the data suggests that they're consistent with one another. You just got to work on your language. So we can't prove mechanisms right, but we can prove mechanisms wrong when our data is not consistent with the mechanism. And so the last thing here, I know I showed you a lot of things. Never on an exam will we ask you to propose a mechanism. We will always give you the mechanism and usually ask you, is the data consistent with one another or something like that. And so let's put all of these examples together with mechanisms and review some of the other methods we used to determine rate laws. Because look, I give you a mechanism and I give you data. And I'm asking, okay, what can we glean from this information? So let's do what we are doing now and look at the proposed mechanism. Let's get a rate law. Tell me the rate law. Rate equals K, NO2, and F2. Is that it? Yeah. Slow step is the first step. Perfect. So based upon that rate law, it's first order with respect to NO2. It's first order with respect to F2. I give you initial rates. When you see tables like this, there's another strategy that we can use to get a rate law, right? Where it's like, oh, if this doubles and you see a doubling in rate in overall rate, that's first order, etc. So we're using these skills again to get the rate law again using this data, and then we'll see if they match. So this is review. Tell me, what trials should I focus on? Trials 1 and 2, yeah, because what's special there is NO2 stays constant, but F2 changes. So I see a tripling in F2. What happens to that initial rate? Also triples. So what does that imply? First order with respect to what? Why F2? It's the one that's changing. So it's implying that F2 is first order. Like, yes, I want you to know it's first order, but apply it to the right one because there's two substances. All right, so I got one of the orders. Am I done? No. What trials do I want to focus on now? 1 and 3, because now F2 stays constant. I see NO2 is doing what? Doubling. And then the initial rate is doing what? Also doubling. So what does that imply about NO2? Also first order. So if this was online homework, which was due yesterday, what would you say the rate law was for this reaction? Rate equals K times NO2 to the first order, F2 to the first order. Great. Okay, now we have two rate laws. What can we say about this data? Is the mechanism correct? No, we can't say that as scientists. Okay, is the mechanism incorrect? No, what we can say is that the mechanism is, or whatever, the data is consistent with the proposed mechanism. All right, that's what we want to say. So yeah, it looks correct, but again, we can't see atoms. All right, let's do another one. I love it, it's all coming together, all coming together. Okay, here's another mechanism, and this time I have integrated rate law stuff. So tell me, what is the rate law given this proposed mechanism? K times NO2, F2, and that's it, because the first step is the slow step. Great. And just like in the previous example, we saw data that suggested that NO2 was first order and F2 was first order. So let's do that same idea, but now with the integrated rate laws, the graphical method, where we use the integrated rate laws to understand how we graph the data. But when we graph data, what kind of data are we looking for when we graph it? Straight lines, yes. So we have straight lines here. So yes, the data is graphed correctly, but what you want to focus on are the y-axis. How is the data graphed? all right, where the straight line and where it's, how it's graphed on the y-axis tells you about the order of that reactant. So we see natural log of NO2 concentration is being graphed, it's being graphed by natural log, and F2 is staying constant, and we see that concentration is changing over time. So what does this graph tell us about the order of NO2? It must be first order, because it's a straight line when it's graphed natural log. If I regraph this data doing 1 over NO2 concentration, will that be a straight line also? No. What if I just graph regular NO2 concentration? Will that be a straight line? No. You'll never find data that's a straight line for all 3 graphing methods. It'll only ever be a straight line for one of them. Okay, so this implies that NO2 is first order. What about the graph for F2? What does it imply about F2? It is second order. Yes, because it's graphed 1 over. Did you memorize that? You did, but do you have to memorize that 1 over is second order? No. Where can you get that information? Yes, from the supplemental, but where on the supplemental? In the integrated rate laws, right? The integrated rate laws, 0th order is when concentrations are like regular. First order is when they're natural logs, and then second order is when they're 1 overs. So, I mean, as long as you know that, then how you graph it technically doesn't need to be memorized, as long as you know it comes from those integrated rate laws. Okay, so tell me, is this mechanism consistent with the experimental data? No, it's not, because we would want a mechanism that is, so rate equals K, NO2 to the first power, and then F2 to the second. That's what we would want. Okay? I think this is fun. All right, last one. Okay, so here's our proposed mechanism. Slow first step, fast first step. Is this mechanism consistent with the reaction coordinate diagram? Yes or no? What are we looking for? Okay, what does a slow step mean? What does it mean about K? If it's slow, K is small. So how do we get small Ks? Big activation energies, yeah. So if you have a small K, there's a large activation energy. What about a fast step? Fast steps have big Ks. Then what about their activation energies? Small activation energies. And this comes from the Arrhenius equation. K equals a e to the negative activation energy temperature, where we see that rate constant, same rate constant that's in our rate law, is dependent on activation energy, bigger hill, slower reaction, or on temperature. If we increase temperature, your particles, the collisions, there's more likely those collisions will lead to getting over that activation energy. So yes, this mechanism is consistent with that, because the first step has a very large activation energy, and then the second step has a very small activation energy. So this is consistent with a 2-step mechanism that's slow and then fast. All right, so I think that's it. That's it for mechanisms, but I hope, it kind of sucks that the midterm one we cut it up, because I think, you know, learning rate laws 3 different ways and seeing how they all relate. We're always talking about the same rate law in all 3 examples, all 3 methods. It's a very comprehensive view of, you know, how fast reactions go, how temperature has an effect, how activation energy has an effect, and yeah, so, okay, that's mechanisms. What method do you like the most? Initial rates, graphing, or mechanisms? Or you don't care, you don't give a crap. You don't care? I like mechanisms, it's fun. It's like a little puzzle. Okay, so let's move on to catalysis. And this is the last way we can make a reaction faster. Why? Why do I keep talking about making reactions faster? It's because as humans, time is money. And if the faster we make a reaction go, the more money we save, the more time we save. All right, the more product we can make and sell, that's why we want reactions to go faster. So let's think about the different ways we can make a reaction go faster. Let's go back to our intuition before we get into catalysis. What are the ways we can make a reaction go faster? Reactants. What are the ways? Increase K. Yeah, we can increase K, but how can we increase K? Do we just tell the reaction, hey, increase your K? No. What can you do? You can change concentrations of your reactants, but does that change K? No, it doesn't, but that is a way we can increase our reaction rate. So if we increase concentration of reactants, rate increases. Didn't we already talk about this, like the very first slide of this chapter, how to make reactions go faster? Increase concentration. We can also increase K, rate constant. But how do we increase rate constant? Let me remind you, EA negative EA over T. What are the ways we can increase rate constant? Increase temperature, yep. Decrease activation energy. Yeah, so this is the last one that we're going to talk about now. Because increasing temperature, I feel like that's something you understand how to do. You increase the heat, okay? But decreasing activation energy, that's a little bit more difficult to do in like a lab setting. Like, how do you do that? And how you do that is give the reaction a new pathway to take to lower the activation energy of that reaction. So the idea here is, like, in lab, to make a reaction go faster, oftentimes what we do is heat it up. What's harder to do is lower that activation energy. How we do that is via catalysis. All right? So catalysis is the only way we can lower the activation energy of a reaction. And I'll show you some examples of catalysis in your everyday life that you've already interacted with, right? We already talked about catalysts in terms of a multi-step reaction. They start off as a reactant, but then they're a product in another step. So they cancel out, they're consumed and then made by the end. All right? So they're not part of the overall reaction, but they still need to be present in order for it to occur. It's usually consumed and then regenerated. It's a reactant, then it's a product. All right, catalysts, how do they make reactions go fast? They either lower the activation energy of your reaction, or sometimes they increase your frequency factor. They increase the effective collisions in your reaction. So those are two ways that catalysts improve reaction rate. Previously, we just talked about temperature, but changing temperature doesn't change how big the hill is. It doesn't change your activation energy. It just changes how many particles have enough energy to get over that hill. But changing activation energy changes how, or adding a catalyst changes how big your hill or your activation energy is. So that's essentially how a catalyst works. So two examples of catalysts that we'll look at is homogeneous catalysts and heterogeneous catalysts. There is a difference. Homogeneous catalysts is a catalyst that's added in the same phase of the reaction. An example would be an all-gas reaction. All right, so if your reactants are gases, your products are gases, your catalyst is a gas, that's a homogeneous catalysis. Or like all aqueous or something, where your reactants are aqueous, your products are aqueous, and your catalyst is aqueous, all dissolved in water. Those are homogeneous catalysts, all the same phase. Versus heterogeneous catalysts is usually the catalyst is a solid, and you add it to a reaction that's a different phase. So it could be like gases, or it could be aqueous, but you're literally adding a solid into that reaction. And when you have heterogeneous catalysts, you really are dependent on the surface area of that catalyst, all right? So heterogeneous catalysts aren't as effective as homogeneous catalysts. You can think of it using collision theory, all right? The only collisions in heterogeneous catalysts is on the surface. But when you have your catalyst in a solution that's completely uniform, those collisions are much, much more, I guess, effective in that case. So what, if you had the choice of doing heterogeneous or homogeneous catalysis, what would you choose? Homo, yeah, it's gonna be a lot faster. All right, so there we go, cool. All right, let's talk about catalysts. Enzymes are catalysts. We'll talk about that in another slide, and I'll do my best to do biology. Okay, so let's think about an example of a reaction that's catalyzed. This is hydrogen peroxide. Has anyone purchased it? Do they have it in their medicine cabinet? Have you seen it at the store? Yes, okay, so hydrogen peroxide undergoes decomposition, where H2O2, so peroxide decomposes into water and oxygen gas. So a gas is produced. Let's think about this. Does this reaction happen on its own in the grocery store when you buy it? Yeah, you might be confused by that question. Think about it. If this reaction goes forward, what's generated? A gas. So if this reaction did happen on the grocery store shelves, what would happen to all these bottles? They would explode with gas. So when you go to the grocery store, do you see them all, puffed out? No. So when they sit on the shelves or they're in your medicine cabinet, this reaction does not happen. It's staying on the reactant side. This is the uncatalyzed reaction, right? Where everything remains as a reactant because this activation energy is so large that your reactants stay on the reactant side, you don't actually go and make products. And that's good. We don't want this reaction to be catalyzed inside the bottle or they would explode. And we don't want that. Okay, but what happens the moment you put peroxide on like blood or a wound on your hand or something, what happens? It bubbles. So your blood is acting as a catalyst, yes. Okay, but I'm not going to use blood. I don't know the chemical formula for that. So we'll use something else. So this is what happens when you put peroxide on a wound or use something as a catalyst. What happens is that you see the bubbling. All right, now you've initiated that reaction to go forward, and the reason is because you've given the reaction this new catalyzed pathway. All right, a catalyzed pathway where the hills are overall smaller. You can tell, yeah, look, those are smaller activation energies. All right, so once you do that, add that catalyst, the reaction does go forward. All right, and so we want that to happen as soon as it hits like, a wound or something to do its disinfecting. All right, so actually, quick question. The uncatalyzed reaction, how many steps is that reaction? 1, because there's one hill. What about the catalyzed reaction? How many steps? 2. So let's look at the 2 steps for this catalyzed reaction. And you see, yes, it is 2 steps. So if we look at this 2-step reaction, what species cancel out? Just name one of them. Br2 cancels out. Yeah, so let's highlight that. Br2, Br2. But what is Br2? Is it a catalyst? It's an intermediate, yes. Br2 is an intermediate because it's produced and then consumed. I never added it into my reaction. Okay, what else cancels out in this reaction? H plus cancels out. H plus is a what? Catalyst, because it is a reactant then product, and then there's actually one more catalyst. Br minus is also a catalyst here. And so you see all those things I highlighted, they cancel out of that reaction, leaving us with the overall reaction. They're doing some stuff behind the scenes to make this 2-step mechanism to give the new catalyzed reaction pathway, to make the reaction go faster as soon as that catalyst is introduced to the reaction. Yeah? Does every catalyst have an intermediate? Yes, it does. And I'll show you an example when we talk about enzymes. Yeah. Yeah. It's only one slide because I can't talk about biology that long. Okay, let's look at the potential energy curve. So you see here are our catalysts, Br minus, H plus, Br minus, H plus. See where they are on this reaction coordinate diagram, right? They live with the reactants and products because they're added like reactants, but they're produced again as products, versus the intermediate that we saw, it only lives between those two reactions. I never added it directly to this reaction. All right. Okay, so there is that. Okay, so let's talk about enzymes, I think. Okay, perfect. All right, yes. So enzymes is also a catalyst, but I want you to think about enzymes in terms of the Arrhenius equation. You know, your biology classes will talk about enzymes much more eloquently than I can. So I want us to think about how does an enzyme operate to not only make reactions, unfavorable reactions go, but relate it to the ideas of collision theory and the Arrhenius equation. So enzymes and biologists, they use funny names for things. So enzyme, that's like your catalyst. Substrate, this is your reactant. All right? Your enzyme and your reactant come together, and then your enzyme releases, it does the reaction, and it releases the product at the end. So biologists, they use the term substrate instead of reactant. Sure. And so the question was asked, when you introduced a catalyst to a reaction, will it always make an intermediate? Let's look at this. Okay, let's look at this. Here, the substrate is the reactant. Here are our products. What do you think this enzyme substrate complex is? That's the intermediate. Yes, that's the intermediate that's produced. I wonder if, I don't know if biologists use that term. Probably not. They call it the enzyme substrate complex, but really what it is an intermediate. It's made in the first step and then consumed in the other step, next step where the products are released then. So yes, you're right. You do make it intermediate at some point there. Okay, so enzymes, so how these work is that there's an active site on an enzyme that has a high affinity for your reactants, either through intermolecular forces, dispersion, all of that. Basically, enzymes have attraction, a certain amount of attraction to the reactants that it's trying to catalyze. And so we call that the active site, and that's how your substrate comes in to lock into that enzyme for a reaction to occur. Substrate, again, is a bio term for reactant. All right, so your reactant has a high affinity for your enzyme. It is able to bring all the reactants close together, increasing the concentration of the reaction occurring, essentially. And so enzymes speed up reactions kind of a multitude of ways. So enzymes, if we think about how it operates, it brings reactants close together. So what this does is essentially increase your concentration, increasing the rate of your reaction because of the rate law, right? Increasing concentrations typically increase reaction rate. And so if enzymes are able to bring and attract substrates together, we increase the concentration. That's how we increase reaction rate. But that's not the only way. Enzymes are also shaped in a certain way, that the active sites are shaped in a certain way that the substrates can only come into that active site in a certain orientation. And of course, enzymes are designed in such a way where that orientation is the correct way, the correct type of collision that we need to make for a reaction to occur. So if we improve orientation, what happens is we improve or increase your frequency factor within our Arrhenius equation, right? So we increase A. And so if we increase A, rate constant also increase our rate, right? And so then the last idea here is enzymes in the active site. Once you have a substrate inside there, because of the high intermolecular forces inside that pocket, it basically pre-weakens the bonds in the substrates. So the reaction can occur faster. So the weakening of bond energy of your substrate, what you're doing, this is how we lower the activation energy, thus increase reaction rate of the process. So this is all the things an enzyme does, and it affects different details of our Arrhenius equation or of our rate law, either increase concentration, improve orientation of our collisions, or lower the activation energy of your substrates. I like to think of enzymes like pre-chew up the bonds of the reaction. Once an enzyme is present, it like pre-chews it up for the reaction to go faster there. Right? And so you can see that here, once this substrate's in the enzyme pocket, it's like has this high affinity for those bonds, pre-weakening them, so this reaction actually occurs. And that's what happens. And so again, just like other catalysts, enzymes also, we're making this new kinetic pathway for the reaction to take that overall has a lower activation energy, maybe is in more than one step, all right, than the original reaction. But overall, this is faster because it has that lower activation energy. All right, so that is my attempt at enzymes. But the big idea here is the utilized collision theory and the Arrhenius equation. So let's talk about what I like to talk about, and that's cars. And so a catalytic converter is another example of a catalyst. Let me go back to enzymes. So enzymes, these reactions are happening in water, things are dissolved, so this is more or less a homogeneous catalysis. Versus in a catalytic converter in your car, okay, what physical state is the exhaust system on your car? It's a solid, but it's catalyzing reactions that are in the gas phase because that's the exhaust that's coming out of your tailpipe. So this is an example of a heterogeneous catalysis because the catalysts are in the solid phase, but they're doing reactions with gases. And so what did we say was better if we had the choice to do catalysis? What would we want? Homogeneous. It's going to be the best. But then why do, heterogeneous at all? It's because, platinum is easier to get in terms of finding a sufficient catalyst that will act with gases. It's hard to find ones in like the aqueous phase or the gas phase to introduce into a car exhaust system, so solid is our best bet. So how we kind of get around the crappiness of a heterogeneous catalyst is to add a lot of surface area. All right, so if you've ever cut open, I hope you've never cut open a catalyst, it has a honeycomb structure. Where if you zoom in here, this honeycomb structure, this is where the catalyst lives, where there's an increase in surface area to facilitate the catalyzed reaction. So that honeycomb or the mesh screen allows for lots of surface area for catalysis to occur. So in a car, all of our vehicles have it. There's about 5 grams of rare earth metals like platinum, palladium, rhodium to catalyze the exhaust coming from your tailpipe. And so just that 5 grams of metal, especially like around here, you hear in the news of all of this like folks stealing catalysts from vehicles because they can just crawl under there, cut the catalyst out to get that rare earth metal. And so I think on the black market, like a stolen hot cat goes for about $300. So just 5 grams of that rare earth metal goes for about $300. So the reason we introduced a catalyst or a catalytic converter in our vehicles is to reduce emissions. That's the big idea for why we have catalysts. This was introduced fairly recently, like within my lifetime, for catalysts to be in exhaust systems, because we think about burning gasoline. It's not just complete combustion. You don't just make CO2 and water. That's not the only thing you make. There's other things in gas too. Sulfur-containing compounds, nitrogen-containing compounds, other bad things that lead to pollution. So I'll show you that. A 3-way catalytic converter actually catalyzes 3 different reactions. They are actually redox reactions. We'll talk more about this in chapter 20. But when you burn gasoline, NOx gas is, comes out of your tailpipe. So NOx just means that there's an X number of oxygens. It could be NO, it could be NO2, NO3, just any number of oxygens. So they call it NOx gas. That's bad. You add this to water, you make nitric acid. That's bad. Carbon monoxide, is that good or bad? That's bad, that'll kill you. Uncombusted hydrocarbons, breathing that in, that sounds bad too. All these things are bad and all these things come out of your tailpipe unless you have a catalytic converter, which is what the new EPA standard is. And so with the presence of this catalytic converter, we see, those NOx gases, they're able to be converted to N2 and O2. Are those things good or bad? I mean, they're better. They're better than nitric acid. N2, that's very present in the atmosphere. Oxygen, very present in the atmosphere. A lot better than nitric acid. Carbon monoxide gets converted to CO2. Ooh, yeah, that's better. I mean, CO2 isn't great, but it's better than carbon monoxide that will asphyxiate you. And then those uncombusted hydrocarbons in the presence of that catalyst convert to CO2 and water. So a lot less bad. All right, that's why we need catalytic converters. I already said, the porous surface area of the CAT is the active site improves surface area. I have a wood burning stove at home, and it has a catalyst too to improve efficiency. And so I've taken it out to clean it, and it too has a honeycomb shaped structure. It's very hard to clean. I have to take a pipe cleaner and poke it through every single hole to get it clean. Yeah, but I want that catalyzed reaction to occur to improve heat output. So that's porous surface area. Last thing here, increasing temperature improves catalytic activity. I love my stories. So I lived in Pennsylvania. Pennsylvania is an emissions check state, the whole state. Who here lives in a county, like Ohio County, that does e-check? Yeah, so you know what I'm talking about. Every year, you have to go to the mechanic, and they have to stick a little thing in your tailpipe and check that you aren't producing all the bad stuff out of your tailpipe. Instead, you need to have be under a certain amount of concentration of the bad stuff to ensure that your catalytic converter is working properly. All right, and so I lived in Pennsylvania, so I had to do that every year. There's some counties here that you have to also do. Is it every year? Wow, that sucks. Yeah. Okay, so here's me in high school. I drove a very old car. It was my first car. It was a third hand-me-down, but it was my fave. So I went in to do my emissions check, and my mechanic said, you failed. All right, this car, it was a 1988 Geo Prism. It was older than me, but it was my favorite car. And he's like, you failed the emissions check. So it's not roadworthy anymore. You can't ride on the road if you don't have the emissions check. You have to be above a certain, or I guess below the limit of noxious gases. But then my mechanic is one of them shady mechanics. Yes. And he told me, he's like, okay, take this vehicle, go drive to the county over 30 minutes, and then drive 30 minutes back. When you're 5 minutes away, call me. And as you're rolling up, he'll do the test. All right? Because the point of that, of driving for an hour straight all on the highway, was to get my engine to get real hot. All right? Get my exhaust real hot, because catalysis is improved if the temperature is really high. So he wanted to get my exhaust system really hot, and then basically I didn't even stop moving, and he did the little test while everything was really, really hot, and thankfully doing that did the trick, and I passed another year. All right, but I think the next year I couldn't pass. But it did get me one more year with that vehicle, and that's the idea of, okay, get your system really hot, improve the temperature. That's when catalysis is gonna work the best. All right, so I like to tell that story because people relate to shady mechanics. But he wasn't shady, got me another year out of it. And then the last thing here with catalysts is, all of this is surface driven, and so if you get any crud in your catalyst, your heterogeneous catalyst in that honeycomb structure, it renders the catalyst useless. And so lead is something that spoils your catalytic converter surface. So when we buy gasoline at the gas station, they call it unleaded gasoline because they used to add lead to gasoline. And so a little bit of lead can really destroy all of those precious metals, catalyzing these reactions. That's probably what happened, to my very, very old vehicle and why it wasn't doing the catalysis it was supposed to. All right, so that's catalytic converters. And enzymes. I talked about both. Okay, so let's do 2 last problems, and that's identify intermediates and catalysts for this 3-step mechanism. So first, what is the overall equation? So just identify what things cancel, add it up. So what cancels? B's cancel, what else? C's, anything else? D. Okay, so you can see that this reaction adds up to 2 A's, make an X. All right, so just be careful of what you canceled here, and that will help us identify, is it a intermediate, is it a catalyst, or is it neither? Okay, so what is A in this reaction? Neither. Yes, it is neither. Technically, A is a what? Reactant. Okay, but then what is B? B is also a reactant, right? No, it's not. This one's different. Yes, B lives on the reactant side of this first step, but overall, it's actually a catalyst because it is consumed and then produced at the end. Yeah, so be careful there. C, what is C? Intermediate. Yeah, don't get mixed up. Don't think that it's a product, okay? Because yes, it's a product in one reaction, but it's a reactant in another. What is D? Also an intermediate. And then what is X? Neither. Technically, it's a what? Product. Yes. So get those straight. Okay. All right, let's do one more. I believe in you. Consider this reaction. It's a 3-step mechanism, but the last step is the slow step. The 3rd step is the slow step. I never taught you that, but do you think you could do it? Probably. Yeah, probably. So, all right, this reaction. If the last step is the slow step, what is my rate law? Is K times what? D times A. Yay! Are we done? No. What do we have to get rid of? D. D is an intermediate. If you add up this reaction, it looks like C's cancel, D's cancel. This is 2A plus B gives you X. So we need to get rid of D. So what equation are we going to use? The 2nd step. So the 2nd step says that rate constant times C, forward reaction, is equal to rate constant times D. So that allows us to replace D concentration with C concentration. All right, so I can shove that in there. So now the rate law is K times C times A. All right, now I'm done, right? No. So what do we got to do next? Get rid of C because C is also an intermediate. So what do you think we'll do? Use the 1st step. Yep, we'll use the 1st step. So recognize that the forward reaction, so rate constant times A times B equals rate constant times C concentration. So it looks like C can be replaced with an A-B concentration term. And so that's the last thing that we shove into that equation to get rid of C. So we see that the rate law is an overall K. Again, I just combined all the Ks. I didn't really keep track of them. Is equal to A squared B. That's it. All right. We gave this third step, slow step, like 2 years ago on an exam, and a bunch of people complained. But no, you have all the skills you need to do it. I could give you a 4th step, slow step, and as long as you keep canceling out the intermediates, then you'll be fine. Yeah. Okay. All right. So that's it. That's it for chapter